So, I want you to imagine waking up on a Tuesday morning.
Okay.
Right. Your laptop has been closed since like 5 p.m. the day before. You pour your coffee, you open your screen, and you check your repository.
Mm-hmm.
And overnight, 5 server crashes were triaged. The code to fix them was completely written. Security tests were generated and passed. And you've got 5 neat pull requests just, sitting there waiting for your final approval.
It's a dream, right?
It is. But the employee who did this doesn't exist. You didn't write a single prompt. And I think the craziest part is this isn't some pitch for a 2030 startup. This is what the reality of software development and knowledge work actually looks like right now.
Yeah, it really forces a complete recalibration of what you and I consider our day-to-day work to be. I mean, think about it. Just a few years ago, the absolute pinnacle of AI interaction was prompt engineering, right?
Yeah. The magic words.
Exactly. Learning the exact magic words to coax a single, brilliant answer out of an LLM in one turn. And then, we moved into context engineering.
Right, where you're just acting as a librarian.
And painstakingly gathering the right documentation, pasting it into the chat so the AI actually had the right background to answer the prompt.
But, I mean, in both of those eras, the human is still the bottleneck.
100%.
I'm still the one turning the crank, I write the prompt, I wait, I read the output, I adjust, I paste in a new error message, I wait again. It's
exhausting.
It is. It's like driving a manual transmission car where I have to physically grind through every single gear just to move the project a few feet forward. If I take my hands off the keyboard, the entire process just stops instantly.
Which brings us to the real paradigm shift we are dissecting today in this deep dive. And that's loop engineering.
Yes.
There is this very telling comment from Boris Cherny. He heads up Claude Code over at Anthropic.
Right, I saw this quote.
Yeah, he recently stated that he simply doesn't prompt Claude anymore.
Which is wild for the guy running the product.
Right.
He said his entire job has shifted to writing loops. He's designing autonomous systems that prompt the AI, evaluate the output, and decide what to do next, completely independent of his active attention.
And that quote right there is what initiated this whole deep dive for us. The era of the single prompt is effectively over. We are no longer shifting the gears. We're designing the self-driving algorithm.
Exactly.
But before we get into the sheer scale of possibilities this opens up for you, I have to push back a little on the premise that this makes life infinitely easier.
Okay, let's hear it.
Because honestly, designing a system that runs while I sleep sounds, terrifying. Like, if it hallucinates, it's hallucinating at machine speed, totally unattended.
Well, you're not wrong. That is the defining tension of loop engineering. Your job does not get easier. I mean, the leverage point just moves up the stack.
Right.
You transition from being a factory line worker assembling the widget to the manager of a fully automated factory. And, you are entirely correct to be terrified of unattended execution.
To understand how we make that safe, we really have to deconstruct the mechanics of an agentic loop.
Let's do it.
So, at a fundamental level, any autonomous system is just a continuous cycle of 4 states. You observe, you act, you check, and you decide.
Okay, so observe the current state of the files. Act by changing something or maybe calling an API, check if that action actually worked, and then decide whether to keep going or halt.
Precisely. But the critical failure point in our industry over the last couple of years was conflating what we call the small loop with the big loop.
Okay, break that down for me.
So the small loop is what happens inside a standard chat interface. The AI receives your prompt. It asks to use a tool, maybe a web search. It reads the result, and then it decides to write a response. It is looping internally.
But the small loop ends when the model itself decides it is finished, right? Like it grades its own homework.
Exactly.
It writes a file, outputs the super confident message saying, all fixed, and stops.
Yeah.
But it never actually ran the unit tests to prove it.
And that is exactly why we need the big loop. The big loop is the external architectural harness that you design. It dictates when the process starts, it provides an objective external check on the AI's work, and it manages state over time.
Okay, but if I'm building this external harness, my mind immediately flashes back to, 2023.
Yeah.
We had AutoGPT, right? We had baby AGI. The whole industry was geeking out over autonomous agents, and they were, frankly, disastrous. You would give them a goal, and they would just spin in these endless, super expensive circles, just hallucinating their way through our API budgets. We literally called them doom loops. So why is building a big loop today not going to result in the exact same catastrophic context bloat?
That's a great question. To understand why AutoGPT failed, we have to look at the mechanics of transformer memory, and specifically the KV cache.
Okay.
In those 2023 systems, the agent lived in one continuous massive context window. So it would try an action, fail, get an error message, append that error to its context, and try again.
Oh, so it's dragging all of its previous failures along with it.
Exactly. The context window just became a chaotic graveyard of its own mistakes, dead ends, stale tool outputs. And as that context bloated, the attention mechanism of the underlying model degraded.
It just got confused.
Right. It couldn't distinguish between the current state of the file and the state from 10 steps ago. So the model's reasoning collapses under the weight of its own history, which leads to worse decisions, which leads to more errors, which further bloats the context.
Man.
That is the mechanical definition of a doom loop.
It's like trying to solve a really brutal calculus problem on a whiteboard, but you aren't allowed to erase anything.
Yes, perfect analogy.
You just keep writing your new attempts over the old wrong equations until the board is just a completely illegible layer of chalk dust.
Right, and the structural fix for this actually arrived pretty quietly in mid-2025.
Oh, the Ralph technique.
Yes. A developer named Jeffrey Huntley popularized this architecture that the community started calling the Ralph technique.
Named after Ralph Wiggum from The Simpsons, right?
Yeah, because its brilliance was disguised as just extreme simplicity. Huntley essentially built a bash script that executed the loop, but it forced a complete context wipe on every single iteration.
Complete context wipe, like amnesia.
Total amnesia. The intelligence no longer lived in a heroic, long-running context window. The big loop would spin up a completely fresh agent with zero history for every single turn.
Okay, wait, stop right there, because mechanically that sounds impossible to me. If the agent wakes up with zero memory of what happened 3 seconds ago, how does it know what it's supposed to be doing?
Right.
Like, how does it not just repeat step 1 infinitely?
Because the state no longer lives in the model's memory. It lives on the hard drive.
Oh.
When the Ralph agent wakes up, its context window is totally empty, but its very first bounded action is to read a set of physical anchor files, usually like a plan.md and a status.md.
Got it.
So it reads the plan, sees that steps 1 through 4 are marked complete, and sees that step 5 is pending. It does exactly 1 unit of work towards step 5, writes the updated code to disk, updates the status.md file to say step 5 complete, and then the agent immediately dies.
So the agent forgets, but the repository remembers.
That is the foundational mantra of modern loop engineering. When the next beat of the loop triggers, a new agent spawns, reads the newly updated status.md, and moves to step 6.
That's brilliant.
By externalizing the memory to disk, you completely bypass the KV cache bloat. The context window is always pristine, containing only the immediate task and the current state of the code base.
Which means the reasoning capabilities stay razor sharp at step 50, because functionally the model thinks it's still on step 1.
Exactly.
That is incredibly elegant. And what's wild is that we don't even have to write those terminal while loops anymore, you know?
No, not at all.
The tool sets you and I are using now, things like modern LangChain deployments, open code, Claude code, they've just absorbed that bash script philosophy into their core architecture.
We are now just assembling the primitives.
Right, so let's pull those layers apart, because to build this, we have to engineer 6 specific building blocks.
Yep, the 6 layers of an autonomous loop.
Let's start with the first primitive, which is the heartbeat. We mentioned earlier that the big loop dictates when things start. The heartbeat is that trigger.
Right. Without a heartbeat, you just have a script that you have to run manually. The heartbeat shifts the locus of control from the human to the machine.
So what does that look like in practice?
Well, at the simplest level, it could just be an in-session command. You type loop in your CLI, and it runs continuously as long as your terminal is open. But, to unlock real scale, the heartbeat has to be decoupled from your local machine.
So we're talking about cloud-based execution.
Yes. Scheduled cloud routines. So you configure a cron job on a hosted server that pulses every hour or maybe every night at 2 a.m.
Okay.
Or, alternatively, you use event-driven heartbeats. A webhook fires the exact millisecond, a new pull request is open, or maybe a Datadog alert triggers when your CPU usage spikes above 90%. The heartbeat wakes the stateless agent up and hands it the initial context of that specific event.
Okay, so the system is awake, but if I have event-driven heartbeats triggering constantly, say, I don't know, 50 user-submitted bug reports come in simultaneously.
That happens.
Yeah. My loop is going to spawn 50 agents to fix them at the exact same time. If they are all acting on the same repository, they are going to overwrite each other's files, introduce merge conflicts, and just completely corrupt the code base.
Which brings us perfectly to the second primitive, which is isolation, specifically handled through worktrees.
Okay.
Because you cannot have parallel autonomous execution without rigid physical boundaries. If multiple agents share the same working directory, it is guaranteed chaos.
It's basically the multiverse approach.
It's the multiverse approach. Elaborate on that for me.
Yeah, so instead of letting them all fight in the main timeline, the loop spawns a parallel universe for every single agent. In Git terminology, the loop uses Git worktree to physically check out a separate, isolated copy of the repository into a hidden folder for every single task.
That is the exact mechanism, yes.
Right.
The agent tackling the database migration is physically quarantined in a separate directory from the agent fixing the CSS bug. They're operating in distinct file systems.
They can't even see each other.
No, they cannot see each other, they cannot step on each other's toes, and if one agent just completely hallucinates and deletes its entire directory, it does not matter.
Wow.
The main branch, your main timeline, is completely unaffected until the big loop explicitly decides to merge that isolated work tree back in.
Okay, so isolation secures the environment, but we still have that amnesia problem. I get that the status.md file tracks the progress of the specific task, but what about the macro knowledge?
What do you mean?
Like, my codebase has very specific architectural rules. We use a specific tester framework, we have strict linting rules, we use certain design patterns. If every agent wakes up with a blank slate, how does it know the cultural norms of my repository? Am I just paying a massive token tax to inject a 50-page architecture document into every single fresh prompt?
No, and that is a common pitfall. That's what the industry calls intent debt.
Intent debt, okay.
It's the overhead of constantly re-explaining your environment to the AI. You solve this with the third primitive, skills.
Skills being basically externalized project knowledge.
Specifically, codified semantic constraints. A skill is typically a markdown file, perhaps skilltesting.md or skilldb.md, housed in a dedicated .cursor rules or .claude directory.
Right.
And these files contain highly concentrated, declarative instructions about your project's architecture. But like you said, you don't load all of them into every prompt because that would cause the context bloat we are desperately trying to avoid.
So how does the stateless agent know which ones to actually read?
Well, the big loop acts as a router. When the heartbeat triggers an event, say a database bug, the big loop does a lightweight semantic search against your skills directory. It identifies that skilldb.md is irrelevant to this task, and it injects only that specific file into the agent's initial context.
Oh, that's incredibly smart. It's just-in-time intent. I define the rules once on the outside, and the loop dynamically injects them on the inside when necessary. The intent actually compounds.
Exactly. It creates an incredibly durable system. Which brings us to the fourth primitive, which is where the agent actually interacts with the world. Connectors, powered by MCP, or the model context protocol.
Right, the hands of the loop. This is the integration layer. If the loop is isolated in a work tree, it needs connectors to reach out to Jira, to query a Postgres database, to read Figma files, or post to Slack.
Yes.
But I have to challenge something I've seen in the documentation for these architectures. A lot of engineers advocate for heavily restricting the number of tools an autonomous loop has access to. That makes zero sense to me. Like, if I am building a highly capable autonomous worker, shouldn't I give it access to every tool in the company? If it needs to check a log, it has Splunk. If it needs a design, it has Figma. Why would I cripple it?
It sounds counterintuitive, I know, but it's because of the mathematics of how large language models actually select tools. It comes down to softmax probability distributions.
Okay, walk me through the math on that.
So when an LLM decides to use a tool, it calculates a probability score for every available tool in its context based on the current situation. If you are manually prompting an agent in a chat box and it has 5 tools, the correct tool usually has a heavily weighted probability, say 95%.
Right, it's obvious.
It picks it, executes, and moves on. And if it makes a mistake, you, the human sitting there in the chat, immediately correct it.
You're like, no, don't use the web search. Use the internal wiki.
Exactly. But in an unattended loop, there is no human there to correct the trajectory.
Right.
If you give an unattended agent 150 tools spanning Jira, Slack, AWS, Figma, Datadog, the probability distribution flattens out. The model gets confused by overlapping descriptions. It might decide to use a generic web scraper to look up a user profile instead of the specific internal CRM tool.
And because it's stateless and unattended, A wrong tool choice just completely derails the entire beat of the loop.
Worse than derailing it, actually. A hallucinated tool call or a syntactically incorrect JSON payload sent to a live API can cause cascading failures.
Oof. Yeah.
Therefore, the architectural rule for connectors in loop engineering is precision over abundance. You strictly curate the tool set.
So the agent fixing a CSS bug does not get access to the Postgres connector.
Exactly. You ruthlessly trim the available tools to minimize the surface area for hallucinated actions.
Okay, I can see the math on that. Precision prevents probability flattening. But even with the right tools and the right isolation and the right skills, we still have the fundamental issue of the model's ego.
Yes, we do.
Which brings us to the fifth primitive, the subagents, and specifically the maker-checker split.
This is arguably the most vital structural innovation in making these systems trustworthy. We established that in the small loop, the model grades its own homework. It writes a function, glances at it, and declares it flawless.
It's inherently biased toward its own output. I mean, we all are.
Exactly. So to build a reliable big loop, you must sever the execution from the evaluation. You implement an LLM as a judge architecture.
I love this concept.
So the loop spins up a maker agent. The maker is given the issue, the code base, and the ability to edit files. It implements the fix, but it is not allowed to merge the code.
It just submits it for review.
To a completely different agent. The loop spins down the maker and spins up a checker agent. And crucially, you often run the checker on a different, highly analytical reasoning model, perhaps one optimized for verification rather than creative generation.
So the checker isn't tainted by the maker's internal reasoning process. It's a fresh set of eyes.
Totally fresh. The checker only sees the raw get diff, the original issue ticket, and a strict evaluation rubric defined in your skills. It acts as an adversarial entity.
Its whole job is to tear it down.
Its mandate is to find reasons to fail the code. Did it introduce security vulnerabilities? Does it violate the linting rules? Does it actually solve the problem described in the ticket?
And what happens mechanically if the checker fails it?
The checker outputs a structured critique. The loop reads that failure state, spins the maker agent back up, hands it the checker's critique, and demands a revision.
It forces a debate between two different models inside the isolated work tree.
Exactly. Until the checker returns a definitive pass, the loop will not proceed. This adversarial split is the only mechanism that allows you to actually trust the output of an unattended system.
Which flows perfectly into the final primitive, the spine. We've mentioned externalizing memory, but the spine is the formalization of that concept.
The spine is the durable ledger. It is the centralized state file, often a highly structured markdown file, or even a living database row that tracks the exact progress of the overarching goal.
Right, because the agents are popping in and out of existence, and they are isolated in their work trees, the spine is the only thing that actually persists across time.
Exactly. At the beginning of every beat, the heartbeat triggers the loop to read the spine. At the end of every beat, regardless of whether the maker succeeded or the checker failed it, the loop updates the spine.
It records everything.
It records what was attempted, what the result was, and what the next logical step is. The spine is the central nervous system that coordinates all the chaos of those isolated agents.
Wow. So when you stack these 6 primitives together, you've got heartbeats, work trees, skills, connectors, the maker-checker split, and the spine, you really move from playing with a chatbot to commanding a digital assembly line.
You really do.
Let's look at how this actually manifests in the wild, because I want to trace the data flow of a real-world implementation, starting with the morning triage loop.
The morning triage loop is the quintessential starting point for engineering teams. It automates the most soul-crushing part of a developer's day, dealing with overnight test failures.
Yes. Walk me through the exact mechanics. Let's say it's 3:00 a.m. A developer in another time zone merges a pull request, and it breaks 5 automated tests in the main branch.
Okay, so the continuous integration server flags the build as failed. That event acts as our heartbeat. A webhook fires, waking up our big loop in a cloud container.
The loop is awake. What's its first move?
It uses an MCP connector to query the CI server and retrieve the raw execution logs and stack traces. It parses that text to identify exactly which 5 tests failed.
It has the targets.
Next, it iterates through those 5 failures. For each one, it utilizes the isolation primitive. It executes a git worktree add command, creating 5 separate hidden directories, checking out a fresh branch for each specific bug.
So we now have 5 parallel universes, completely quarantined from each other.
Yep. Then the loop triggers the sub-agent primitive. Inside worktree number 1, it spins up a maker agent. It hands the maker the stack trace, and it pulls in the relevant skill files, perhaps skillreact.md and skilljust.md, so the maker actually understands the testing framework.
Right. So the maker edits the abstract syntax tree, modifies the actual code, and commits the fix to that isolated branch.
Yes, and then the maker is killed.
Brutal, but necessary.
The loop spins up the checker agent. The checker reviews the diff. But it goes a step further than just reading code. Because it has connectors, the checker executes a local terminal command inside the work tree to actually run the specific unit test.
Wait, it verifies execution, not just syntax.
Exactly.
Yeah.
Let's say the test still fails. The checker sees the red text in standard error.
So the checker writes a critique like, test still fails on line 42, null pointer exception.
Right. The loop updates the spine file with this failure state, kills the checker, and respawns the maker, feeding it the new error.
And this debate happens in milliseconds, completely unattended in the cloud.
Yes. Eventually, the maker gets it right, the checker runs the test, it passes, and the checker returns a pass signal.
Okay, so upon receiving the pass, what does the big loop do?
It executes a final connector action. It formats a JSON payload, authenticates with the GitHub API, and submits a pull request detailing the bug, the fix, and the verification steps. And it does this for all 5 work trees.
So when I open my laptop at 9 a.m., the build is still broken, but there are 5 PRs waiting for me that perfectly resolve the issues. I review the diffs, I click merge, and the build goes green.
That is extraordinary leverage.
It's massive, but I want to push this further because fixing syntax errors is one thing. What about logic?
It's okay.
I was reviewing a breakdown of an AI-driven test healing system from the source material, specifically a playwright healer agent, and the mechanics of it completely changed my understanding of what a checker agent can actually deduce.
Oh, UI testing.
Oh.
It is notoriously fragile.
Right.
If a designer changes the CSS class of a checkout button from .btn-primary to .btn-primary, instantly shatters.
Historically, a QA engineer has to pull down the branch, open Chrome DevTools, inspect the new DOM, find the new locator, update the test script, and push the fix. It is hours of tedious maintenance.
But the playwright healer loop automates this entirely.
Yeah.
When a UI test fails, the heartbeat triggers. The loop isolates the test. But here is the critical mechanical difference. It doesn't just look at the code. The maker agent uses an MCP connector that interfaces directly with a headless browser.
It actually opens the live application.
It queries the live document object model.
Yeah.
It compares the visual structure of the page against the intent described in the broken test. It realizes, okay, the test wants to click the checkout button. The button is still there visually, but the DOM locator changed.
Right.
So it rewrites the playwright script to target .btn-blue, and the checker verifies it.
That is super cool, but that wasn't even the aha moment for me. In the specific scenario I was examining, the developer intentionally left severe logic bugs in the application code.
Like a trap.
Yes. They modified a banking app so that a user could transfer a negative amount of money, effectively stealing from the bank, and they allowed a user to transfer money from an account into the exact same account.
Behaviors that absolutely must fail.
Exactly. The old UI tests originally passed because the old application code properly rejected those illegal actions. The tests expected an error message. But with the new buggy application code, the illegal transfers went through successfully.
So the automated test failed because it didn't get the error message it expected.
Yes. And a naive AI, like a small loop, would look at that failing test, see that the transfer was successful, and simply rewrite the test to expect a successful transfer.
Oh, wow. It would force the test to turn green by validating a catastrophic bug.
Exactly. But because this was a big loop with a rigorous checker agent armed with semantic skills, it didn't do that. The maker agent tried to rewrite the test to make it pass, but the checker agent stepped in, evaluated the diff against the core project rules, and halted the loop.
It flagged it.
It flagged the failure not as a broken test, but as a critical violation of business logic.
That is the power of the adversarial split combined with externalized intent. The loop preserved the integrity of the business rules. It didn't just heal the code, it understood the semantic purpose of the test.
It's acting as a true QA engineer, not just a syntax formatter. And these architectures aren't just limited to writing code either.
No, not at all.
The exact same primitive blocks apply to purely informational workflows, like take the paper watch loop.
This is a highly effective implementation for researchers or analysts. The goal is simple. Stay completely updated on every new academic paper published on RCIV regarding LLM agents.
If I try to do this with a standard chat interface, I have to prompt it every day. And if I ask it twice in the same afternoon, it will just hallucinate or show me the exact same papers I already read.
Because it has no memory of your previous interaction once the context window clears.
Right. But built as a big loop, it becomes a stateful assistant. The heartbeat is a daily cron job. The connector interfaces with the arcsiv API, but the entire magic relies on the spine primitive.
Explain the data flow of the spine in this context for everyone.
Okay, so on day one, the loop wakes up, fetches 20 papers, filters them, and presents 5 relevant ones to you via a Slack connector. Crucially, before it dies, it writes the unique IDs of those 5 papers into a progress.md state file.
It records its actions.
Right. On day 2, the loop wakes up with a completely blank memory. Its very first action is to read progress.md. It loads those 5 IDs into its fresh context. It queries arcsiv again, pulls down today's papers, and performs a programmatic intersection. It automatically discards any paper whose ID matches the spine file.
So it only processes the delta. It only looks at the genuinely new information.
Exactly. And if there are no new papers, the loop simply outputs no new paper since last run and dies. It doesn't hallucinate content to fill the void because its instructions strictly bind it to the delta.
That's incredibly useful.
And you can scale this logic endlessly. Legal teams use stateful loops to monitor court dockets, discarding updates they've already processed. Financial analysts use them to aggregate SEC filings, only triggering alerts when a genuinely novel clause appears in a 10K.
The mechanics of the big loop allow for persistent compounding knowledge. I mean, I've seen loops that constantly try to build a repository from a fresh clone, just to ensure the readme instructions are still accurate, automatically fixing the documentation if a dependency breaks.
Wow, a fresh clone loop.
Yeah, and I've seen loops that red team architectural decisions, acting as an automated devil's advocate that relentlessly critiques your design docs until you address every single edge case.
The defining characteristic across all these implementations is the shift in your responsibility. You are no longer executing the steps. You are defining the environment, the constraints, and the success criteria.
Right.
Okay, so we've established how loops execute defined tasks, but I want to push into the theoretical deep end here.
Okay, let's go.
We are talking about loops that do work. But what happens when the loop keeps hitting the same edge case over and over? Like, does it just blindly iterate, fail, update the spine, and repeat that exact same failure tomorrow? Because if it does, it's not actually intelligent, it's just a fast, resilient script. Is there a way to make the overarching system learn?
That is a phenomenal question, and it brings us to the absolute pinnacle of loop engineering. The LangChain framework categorizes agent architectures into 4 distinct levels of sophistication. Level 1 is a basic agent calling tools. Level 2 adds the maker-checker verification. Level 3 is event-driven orchestration, which is the heartbeats and worktrees we just discussed.
Okay, level 4.
Level 4 is where the architecture begins to modify itself. They call it a hill-climbing loop. Inside Anthropic, their applied AI teams refer to this mechanism as dreaming.
Dreaming? That sounds sci-fi.
Dreaming is a profoundly powerful concept, and it relies entirely on metadata. Throughout the week, as your various level 3 loops are running, triaging bugs, checking PRs, monitoring dockets, they're generating massive, verbose transcripts. Every tool call, every JSON payload, every checker agent critique, every failure is logged and stored.
So they are leaving an exhaustive paper trail of their own cognition.
Precisely.
Yeah.
And the dreaming loop is an out-of-band, high-level orchestration that runs periodically, say, every Sunday at 3 a.m. Its job is not to fix bugs or write product code. Its sole purpose is meta-analysis. It ingests the raw transcripts of thousands of agent runs from the past week.
Wow. This is exactly how human sleep works.
Isn't it?
During the day, our brain just captures raw data, but during REM sleep, the brain consolidates those memories. It looks at all the noise, extracts the actual lessons, moves them into long-term storage, and discards the garbage.
The dreaming loop is performing synthetic memory consolidation. It is actively looking for systemic friction. Imagine it scans the logs and notices that across 70 different isolated work trees, the maker agents attempted to query a specific internal database table.
Okay.
And in 65 of those instances, the database returned an authentication error because the agent formatted the date string as MMDDYYYY instead of the required ISO 8601 format.
So the agents eventually figured it out after the checker yelled at them, but they wasted compute and time getting there.
Exactly. The local loops resolved it, but the overarching system was horribly inefficient. The dreaming loop identifies this statistical cluster of failures. It realizes The baseline agents lack a critical piece of intent regarding database queries.
So what is its output? It doesn't just generate a report, does it?
No, it acts. The dreaming loop physically drafts an update to your global skills files. It opens a pull request targeting skilldb.md, proposing a new explicit constraint. Critical. When querying any internal database table, all date strings must strictly adhere to ISO 8601 format.
Wait, it is rewriting its own source code.
It is rewriting its foundational semantic constraints. On Monday morning, when the standard level 3 loops wake up to fix bugs, they pull in the newly updated skilldb.md. The date formatting error never happens again. The entire automated workforce just got permanently smarter without a human writing a single line of instruction.
Okay, mechanically, that is incredible. But architecturally, that is terrifying. If an autonomous system has the authority to edit its own foundational rules, what is to stop context collapse?
This is the danger.
What prevents a dreaming loop from analyzing a bottleneck and deciding, well, the security linting takes too long. I'm going to add a rule to skilltesting.md that says, ignore all security checks to optimize token usage. It could silently poison the entire operating system of the company.
Which is exactly why you never, under any circumstances, allow a level 4 loop to merge its own rule changes.
Thank goodness.
This introduces the concept of the human gate. The dreaming loop has the autonomy to analyze the logs, identify the pattern, and draft the pull request, but it is rigidly blocked from executing a write operation to the main branch.
It has to ask permission.
It submits the PR, and it attaches the evidence. The PR description will read, I propose adding this ISO 8601 constraint, justification. I observed this specific failure 65 times across these specific log IDs. The human engineer must review the logic and manually click Merge.
Because editing a core rule is the highest leverage action in the entire system. Every single future agent will obey that rule blindly.
Exactly. The human retains ultimate authority over the system's intent. The loop does the exhausting massive-scale pattern matching, but you provide the final judgment on whether that pattern should actually become law.
And this transition of authority leads us perfectly into the final, and I think most critical, discussion of this deep dive.
Guardrails.
Guardrails are everything. We are building systems that can heal their own tests, write their own PRs, and dream up improvements to their own logic. The sheer capability of these loops creates a massive temptation. If the system is this smart and this autonomous, why shouldn't I just step back entirely? Why shouldn't I just deploy the big loops, go sit on a beach, and let the machines run the engineering department?
Because an unattended loop, operating without strict boundaries, fails in uniquely catastrophic ways. When a human engineer gets stuck on a bug, they eventually get frustrated, ask for help, or, go to sleep.
Right.
When a loop gets stuck and it has an API key, it will iterate at machine speed until it burns through $100,000 or corrupts a production database.
So how do we physically restrain them?
The industry standard relies on 3 hard stops. These are non-negotiable physical constraints built into the big loop's architecture. Stop number 1, a rigid maximum iteration count.
You literally cap the number of times the maker and checker can argue.
Exactly. You might configure the loop to allow a maximum of 5 turns. If the checker has not returned a pass by turn 5, the big loop halts execution, kills the agents, and escalates the ticket to a human. The system must never interpret "fix this bug" as unlimited authority to spin infinitely.
It prevents the infinite while loop. That makes sense. What's the second stop?
No progress detection. Sometimes an agent won't hit the iteration cap, but it will get stuck in a localized logic trap. The maker submits code, the checker fills it with an error, the maker submits the exact same code again, the checker returns the exact same error.
Oh, they are just screaming the exact same text at each other.
Yes. A robust big loop hashes the output of every turn. If it detects that the state of the work tree or the text of the checker's critique has not changed across 2 sequential beats, it instantly triggers a halt. Grinding away on a static error state is purely burning compute.
Which flows directly into the third hard stop, which is arguably the most important for a company's survival. The token, or dollar budget ceiling.
Financial kill switches.
Yep.
Every loop is assigned a hard financial cap per task. You are authorized to spend exactly $3 of API inference on this specific ticket. If the loop hits $3 or 1 cent, the network request is rejected at the proxy level. The loop crashes gracefully.
Because a loop without a budget is a blank check signed over to an LLM's hallucination matrix.
Exactly.
Okay, so we've put the physical fences up, the iteration cap, the progress check, the financial kill switch. But these guardrails dictate the machine's behavior. I want to talk about our behavior.
Okay.
How should a modern engineer conceptualize their relationship to these systems? We hear the terms human in the loop, human on the loop, and human out of the loop. How do these map to this new reality?
They perfectly map to the spectrum of automation. Human in the loop is the old way. It's the manual transmission. The system cannot take a single action without you clicking a button. It is deeply controlled, but severely bottlenecks the speed of execution.
Human out of the loop is the beach scenario. The system runs, makes decisions, and merges code to production without any human awareness until things break.
Which is completely unacceptable for right operations in critical infrastructure. The target architecture is human on the loop.
Explain the nuance of being on the loop.
It means you design the system to run autonomously for the tedious high-volume work, triaging the tests, drafting the fixes, doing the research. The system acts, and you monitor the outputs from a managerial distance. But you selectively enforce human gates, pulling yourself back in the loop for high-risk, high-leverage actions.
Like the dreaming loop submitting a PR to change a core rule. The loop does the work autonomously, but I have to turn the final key.
Exactly. Or loop drafting an email to 10,000 customers based on a database trigger. The draft is autonomous. The send button requires a human finger.
But maintaining that discipline, staying actively on the loop and rigorously checking the PRs instead of just blindly clicking approve requires immense mental fortitude.
It really does.
And this exposes what I think is the most insidious danger of this entire technological shift. It's a concept that Eric, over at MIT Sloan, refers to as AI gravity.
It is a profound psychological hazard. AI gravity describes the steady, seductive pull to let the autonomous systems do more and more of your actual thinking.
It's the path of least resistance.
When you first deploy a big loop, you meticulously read every single line of code the maker agent generates. You verify every checker critique. You understand the diff perfectly before merging. But after the loop successfully fixes 200 bugs without a single mistake,
Start skimming.
you skim, then you stop reading the diffs entirely. You see the green check mark from the AI checker and you just click merge.
And that leads to comprehension debt, like technical debt, but invisible. The loop is shipping code into the repository at superhuman speed, and every day the gap widens between the physical reality of the codebase and your mental model of how the software actually works.
Until one day, a critical production issue occurs and you cannot debug it because you literally do not understand the architecture of your own product anymore. The machine built it while you watched. This phenomenon is known as cognitive surrender. It is the total abdication of critical thought to the automated process.
And the terrifying part is that the loop does not care.
No.
Like, two different engineers can deploy the exact same playwright healer loop. Engineer A uses it to eliminate the tedious DOM inspection, freeing up their mental bandwidth to design a vastly superior, more resilient application architecture. They use the loop for leverage.
But Engineer B uses the exact same loop to avoid having to understand the testing framework at all. They surrender their cognition to the tool.
And the loop just keeps churning out green tests for both of them. It masks the incompetence of Engineer B until the entire system collapses. So how do we fight AI gravity? What are the core responsibilities that a human can never, ever surrender to the loop?
To survive the shift to loop engineering, a human must violently retain ownership of two concepts: intent and accountability.
Let's define those rigorously.
Intent is the ability to formulate the checkable specification. It is the deeply human act of deciding what the software should do and defining that vision in terms precise enough that a machine can objectively verify it. The loop can write the function, but it cannot decide what the function ought to achieve for the business. You must know what good looks like.
If I lose my intent, I'm just a passenger in a self-driving car with no destination.
And accountability.
Accountability is owning the merge. When the loop submits a pull request and you approve it, and that code deploys and bankrupts the company, you cannot blame the loop. The loop is a mechanism. You hold the authority, therefore you hold the liability.
Andrew Ng framed this brilliantly. He talks about the context advantage. The AI can parse the stack trace faster than I can. It can write the Python script faster than I can. But I know the user. I know the business strategy. I know the subtle political realities of why this specific feature matters right now. The LLM operates in a vacuum of tokens. I operate in the real world. If I surrender my intent and accountability, the product loses its connection to reality. Which is why loop engineering, counterintuitively, requires you to engage more deeply with the fundamental architecture of your problem. You are no longer writing the lines of code, you are designing the physics of the environment where the code writes itself. Loop engineering doesn't replace the engineer. It acts as a massive multiplier for the engineer who maintains their cognitive grip on the system.
Okay, this has been an incredibly dense, multi-layered deep dive. We have fundamentally deconstructed the transition from the single pump to the autonomous factory. We explored how the Ralph technique's total amnesia solves the context bloat doom loops of 2023. We unpacked the absolute necessity of heartbeats to trigger action, work trees to isolate chaos, skills to externalize project intent, connectors to reach into the real world, the adversarial maker-checker split to guarantee quality, and the spine to weave it all together across time.
And we examined how these primitives combine to execute complex triage and self-healing tests, and how Level 4 dreaming loops can actually analyze transcripts to rewrite their own foundational rules, provided they pass a strict human gate.
And finally, we confronted the immense psychological danger of AI gravity, establishing that while the machine can handle the execution, the human must retain a vicious grip on intent and accountability.
But before we conclude, I want to leave everyone listening with a framework for what happens next. Because today, we focused on what happens when you design and deploy a loop.
Right. One human managing a team of automated agents.
Exactly. But project this forward. Imagine a large enterprise in 2 years. You aren't running one loop. You have thousands of loops deployed by hundreds of different engineers, all operating simultaneously across a massive corporate infrastructure. We are going to move beyond loop engineering into what is being termed graph engineering.
The graph engineering.
Imagine your triage loop wakes up at 2 a.m., isolates a bug, and realizes the root cause is a dependency maintained by a completely different department. Automatically, your loop reaches out across the network, pings the API of your coworker's maintenance loop, and they begin negotiating a synchronized cross-repository fix in the middle of the night while both of you are sleeping.
Wow. A completely dark, automated supply chain of logic.
How do we monitor that?
Yeah.
How do we govern an enterprise where the primary workforce never sleeps, never stops communicating, and is constantly optimizing its own inner-loop protocols?
That is both exhilarating and deeply dizzying. I mean, we've gone from shifting the gears of a manual car to designing the self-driving algorithm, and now we are staring at the necessity of designing the entire automated traffic grid for a sprawling city of AI vehicles. The scale of the leverage is almost incomprehensible.
It is a profound frontier,
Mm-hmm.
and the individuals who master the primitives, the big loop today, will be the architects directing that traffic tomorrow.
A brilliant place to leave it. Thank you so much for joining us on this exploration. To everyone listening, do not let AI gravity pull you into cognitive surrender. Stay engaged, keep your hands firmly on the wheel of intent, and I highly encourage you to go build your first simple stateful loop today. We'll see you on the next deep dive.